Chapter 2, Section 2. We have three topics in this section. The first one is center of mass and center of gravity. The second one is about rotational equilibrium. And the last topic in Section 2 is moment of inertia. Center of mass simply is the point which all of the mass of the object is considered to be concentrated at. So it is simply the point which we can balance the object. Simply have your pen, pencil, anything around you, try to balance it. And the point where you can balance that object is center of mass. When the object is balanced, it is said to be in equilibrium. We'll talk about this one later. We can also find the center of mass by two different ways. We have two types of objects. We have regular objects and irregular objects. For the regular objects, it is very easy and very simple. The geometrical center of any regular object is simply the center of mass, like a triangle, a cube, a donut, an ice cube. These are all regular shapes, so their geometrical center is the center of mass. What about irregular objects? The center of mass is away from the geometrical center toward the heavier side all the time. You have the bat, which is near the center toward the heavier side. And another example is the bowling ball. Again, it is near the geometrical center, but away from the holes. We also have another point, which is called a center of gravity. So what is center of gravity? It is the point where the gravitational force acts on the object. Actually, gravitational force acts on every point, but we have to choose a point. We choose the center of gravity. And in all our examples, the center of gravity is same, is equivalent to the center of mass. So for every example in our book, the center of mass and center of gravity are the same point. So why do we need to study center of mass? Because of two reasons. First, if you rotate any object, of course, you have rotation, so you need an axis of rotation. Remember that. And if I rotate any object freely in air, you have not determined any axis. So it will rotate around the center of mass. When we rotate an object in air freely, we will have two types of motion. The first one is the motion of the center of mass. The second one is the motion of the ends. The center of mass will follow a parabolic path because center of mass will be the axis of rotation, and axis of rotation does not rotate. It will simply have a translational motion. Or we can say that it will follow a path of projectile, like a projectile motion that you have studied in grade 11. For the ends, they will rotate around the axis, which is the center of mass. So that's why we need to study center of mass. The second point, or the second reason that we are studying the center of mass is because if I want to hold any object like that, for example, let's have the pencil that you are writing with and hold on to one of the ends. It can be a ruler, it can be any object. If you hold it on this side, make this one to be the axis of rotation, what will happen when you drop it? It will rotate freely. Why does it rotate? Because there is a torque acting on it, so it will start to rotate. Since it is rotating, there is a torque acting on it. For torque, what do you need? You need force and you need distance. So what is the force that's rotating this object? It is the gravitational force. Okay, where should I draw the gravitational force? Should I draw it at the end? Or should I draw it here? Or should I draw it here? We have to draw it exactly at the center of mass. So I have to draw this one exactly in the middle. You'll need this one for the next topic's questions. And if the distance, let's say, is 3 meters, all of it, so the distance in which the force acting or producing a torque will be 1.5 meters, which is half of it, because it is exactly the center of mass of this object. So I need to know the center of mass to know the distance of the gravitational force that's acting or rotating this one. The next topic is equilibrium. If you remember, Section 3 of Chapter 1, we talk about Newton's first law. In Newton's first law, we learned two lessons. The first one was the equilibrium, and the second was inertia. The first part, which is equilibrium, was whenever the net force acting on an object is equal to zero, the acceleration will also be equal to zero. The velocity is either equal to zero or velocity is constant. So this is not speed, this is velocity. Both magnitude and direction must be constant to be in equilibrium. So what do you mean by being the object in equilibrium? It means there's no change happening to the state of motion. This is called as translational equilibrium. Please remember this. Translational equilibrium doesn't mean that you have translational motion. It means that there's no change happening to the state of translational motion. If you don't have any change, it is in equilibrium. If you have a change, you don't have any equilibrium. So is it possible to have the same equilibrium in rotational motion? Yes, it is possible to have the same in rotational motion. We will say that if net torque acting on the object is equal to zero, alpha will be equal to zero, which means that omega is either zero or omega is constant. So it means that there is no change happening to the rotational motion of the object. If we don't have any change in the state of rotational motion, it is called as rotational equilibrium. So what happens if I have both equilibriums at the same time? We'll have complete equilibrium. So this will be called as first condition, and this will be called as second condition. If I have both, then I'll have equilibrium. Or sometimes we'll call it as complete equilibrium. Let us have some examples for both cases. The first one, a bicycle wheel rolling along a level highway with a constant speed. Let's analyze this. A level highway means that the road is a straight one. It means there is no change in the direction. So direction is constant, and the speed is also constant, so velocity is also constant. So V is constant. Since velocity is constant, omega is also constant. Because V is constant, net force is equal to zero. Because of omega being constant, net torque will also be equal to zero. Since net force is equal to zero, the object is in translational equilibrium. Since the net torque is equal to zero, this object or the wheel is in rotational equilibrium. Since we have both, it is in complete equilibrium or simply equilibrium. The second example is a parked bicycle. Since the bicycle is parked, both V and omega are equal to zero. Since V is equal to zero or velocity is equal to zero, net force is equal to zero. So it is in translational equilibrium, omega is equal to zero, and then net torque is equal to zero, so it is also in rotational equilibrium. So since we have both, it will be in complete equilibrium or simply equilibrium. For the third example, we have a football that's traveling through air. Anything that is traveling in air or anything that's in free fall will only and only be in rotational equilibrium because the gravitational force acting on it. So F net is never zero if anything is in free fall or anything is traveling in air. So the fourth example is a braking tire of an automobile. When you are braking, the velocity will decrease. As a result, omega also decreases. And since velocity is decreasing, net force will be greater than zero. Since omega is decreasing, net torque will be greater than zero. So it is in none of the equilibriums. So it is not in translational equilibrium. It is also not in rotational equilibrium. So it is none of them. The last example that I will talk about is pushing a desk on both sides. Let's have a desk, and you'll apply a force on this side. I will apply the same force on the other side. So this is F, and this is F. And they have the same magnitude, but opposite direction. It is acting on different sides, in different points, not the same point, because we have a question in our book which is talking about acting two different forces on the same point, but this one is on different sides. In this example, the net force is equal to 0, but net torque is greater than 0. Since net force is equal to 0, this object is in translational equilibrium, but it is not in rotational equilibrium. Remember that, please. Now let us solve some calculation questions about equilibrium. First, I will write all the steps that you need to solve the calculation questions in the equilibrium one, and then I will solve 3 different problems by using each step. First one is you need to read the question carefully and then draw a straight line. Second, you have to pinpoint all forces that's acting on the object. And remember that all supports are upward and all weights or gravitational forces are downward. After that, follow the instructions of the question and draw all extra given informations. After that, you need to determine the axis. This is the most important step, which you cannot go or you cannot solve the question without determining the axis. A hint for you in determining the axis: if you had 2 supports, one on the left and one on the right, if the question was asking you to find the force on the right, choose the left one as the axis. If it was asking you to find the force in the left one, choose the right side as your axis of rotation. If it is asking for both, you can choose any of them. It will give you the correct result. After that, you have to determine the distance of each force from the axis of rotation that you have chosen. Calculate each torque and determine the directions. After that, apply the net torque is equal to 0 and net force equal to 0. Different questions will need different approaches. Sometimes you have to use net torque is equal to 0 at the beginning. Sometimes you have to do it later. Some other points for you. If you have 2 unknown forces, you have to use the net torque. If you have 1 unknown force, you have to use net force equal to 0. But if distance is unknown, you can only find it using net torque is equal to 0, because we don't have distance in net force. For the mass, sometimes you have to use net force is equal to 0. Sometimes you have to use net torque is equal to 0. But most of the time, you will use net force is equal to 0. It depends on the question. Let us solve some examples. A man weighs 720 Newton, stands on a light board of length 2 meters that's fixed on 2 supports at its extremities. So, support means the forces are upward, but extremities means that it is N. So, let me apply the first step, which was drawing a straight line. And now I will apply all forces. I have 2 supports at both ends. So the supports are upward. If the distance between the point where the man stands and the first support is 0.5 meter, what is the force exerted by the first support? I will name this side as first support, and I will name this side as the second support. And since the man weighs 720 Newton, I will draw it downward because every weight is downward. From the first support, it is 0.5 meter. All of the length is 2 meter. It is a light board, so the mass of the board is not important, so we don't have weight of the board. If I had it, I would have drawn it at the center, which I'll have in the next example, but we don't have it in this one. So there is no weight for the board, I mean. Now, I have completed the question. I need to choose an axis. The question is asking us to find F1. So I will be choosing F2 as the axis of rotation. And now I need to determine the distance of every force from the axis of rotation. So the distance of F2 is already equal to 0. Always start with the point where you choose the axis as. And distance of the man from the axis of rotation is 2 minus 0.5 will be equal to 1.5 meters. The distance of F1 from the axis of rotation will be equal to 2 meters. Now let us calculate the torque of each force. The torque of F2 will be equal to 0. The torque of the man will be equal to force multiplied by distance, which is equal to 720 Newton multiplied by 1.5, which is equal to 1080 Newton meter. The torque applied by F1 is equal to F times D, which is equal to the force as unknown. I will just write F1 multiplied by 2, which is equal to 2F1. Now I need to talk about their directions according to the axis that I have chosen. The direction of F1 will be clockwise. I mean the torque of F1. I have a pencil like this. Hold it on this side because I have chosen the right side as an axis of rotation, and apply a force in the same direction as each one. Now F1 is upward, so when you apply a force that's upward, the torque of F1 will be clockwise. This one is negative. And then apply a force that's downward, which stands for the torque of the man, which will be rotating the object in the clockwise direction. So this will be positive, and add a negative here, add a positive here, and add all of them. So net torque will be equal to 0, which is equal to 0 plus 2 F1 minus 1080. Now bring the 1080 to the other side. So 2F1 will be equal to 1080 to be positive. Divide both sides by 2. And you will get F1 as 540 Newton. What would we do if it is also asking for F2? This time we'll use the net force that's equal to 0. We have a force that's upward, which is F1, and this is F2, which is also upward. We have the force of the man, which is downward. You can say that the net force is equal to 0, or directly you can say upward forces will be equal to downward forces. How many upward forces do we have? We have 2, F1 plus F2, which is equal to downward forces, which is, I have a single one, which is F of the man. If you use the net force right away, you have to include the downward force as negative. So you will say F1 plus F2 minus F man is equal to 0. But if you say F upward is equal to F downward, you don't have to add any negative to any of the numbers or forces. So F1, we found it as 540 Newton plus F2, which is equal to F of the man, which is 720 Newton. Take this one to the other side. F2 will be equal to 720 minus 540, which will be equal to 180 Newton. Apply these steps to every type of question. No matter how complicated the question is, you will still get the answer perfectly. Let us have another example. In page 42 of the book, Practice 2B, question 2 is talking about a 700 Newton window washer that's standing on a uniform scaffold supported by vertical ropes. See, support means it is upward, 700 Newton washer, which is the weight of the man, which is downward. At each end, the scaffold weighs 200 Newton. This time, the weight of the scaffold is important, and it is 3 meters long. What's the force in each rod? So I have to find both when the window washer stands 1 meter from one end. Again, apply the first step, draw a straight line, and supports at both ends. Apply two forces that are upward. Name it as F1 and F2. The weight of the scaffold is always at the center because it has to be drawn at the center of mass, which is the center of gravity. So this is the force of the scaffold, and it is all 3 meters long. So this side is 1.5 meters. This side is also 1.5 meters. The man is standing, or the window washer is standing 1 meter from one end. No matter which end you choose, you will still get the correct answer. So 700 Newton, and the scaffold was 200 Newton, and this is 1 meter. So I have to choose an axis of rotation. You can choose any side as axis of rotation. I will choose the left side as axis of rotation because it is much easier to calculate the distances in my configuration. But if you draw the man on the right side, you can choose the right side as your axis of rotation. Can I, in this configuration, choose the F2 as the axis of rotation? Yes, you can choose F2 as the axis of rotation. So if you choose F2 as axis of rotation, first you'll find F1. But if you choose F1 as the axis of rotation, first you'll find F2. So the distance of F1 is equal to 0. And the distance of the window washer is equal to 1 meter from the axis that I have chosen. The distance of the scaffold is equal to 1.5 meters, as you see, and the distance of F2 is equal to 3 meters. Now I can calculate each torque individually. The torque applied by F1 is equal to 0 because the distance is equal to 0. The torque applied by the window washer will be equal to the force multiplied by the distance, which is equal to 700 Newton meter. The torque applied by the scaffold on itself will be equal to the weight, which is equal to 200 Newton, multiplied by the distance, which is 1.5 meters. It will be equal to 300 Newton meter. After that, the torque of F2 will be equal to the force, which is unknown. I will write it as F2 multiplied by the distance, which is 3. I will have 3F2. Now I can talk about the directions. Again, have a pen, and this time pinch it on the left side. This one, apply a force upward. You'll see that it will rotate it in the counterclockwise direction. So the torque of F2 is equal to plus 3F2. The torque of the scaffold is trying to rotate it in the clockwise direction. The torque of the window washer is also trying to rotate it in the clockwise direction. Add all of them. So net torque must be equal to 0. They must be equal to 0 minus 700 minus 300 plus 3F2. These two are minus 1000. Take it to the other side. So you will have 3F2 is equal to plus 1000. Divide both sides by 3. And you will get the answer as F2, which is equal to 333.33. It goes on like this. This part is not important. For the next part, we need to say F is equal to 0. If you say that, downward forces must be negative and upward force must be positive. But I will be saying that upward forces will be equal to downward forces, and upward forces are F1 and F2, which is equal to downward forces, which is the force of the window washer plus the force of the scaffold. F1 is unknown. F2 we found it as 333.3 is equal to weight of the window washer is 700 Newton and the weight of the scaffold is 200 Newton. Please remember that it's not 300 because we are talking about the force. The 300 was the torque. And take the 333 to the other side. So F1 will be equal to 900 minus 333.3, which is equal to 566.7 Newton is the answer for F1. Another type of question in section 2 for equilibrium is that of the seesaw question. It is saying a 400 Newton child and a 300 Newton child sit on either end. This is important. So the forces which are downward because they are gravitational force, they will be drawn at the end of the seesaw, which is a 2-meter long. And where along the seesaw should the pivot be placed to ensure rotational equilibrium? Pivot means the axis of rotation. So where should be the axis? To start this one, we will draw a straight line, and then I will draw the forces on either end. Now, I will draw the 400 Newton child on the right side, and I will draw the 300 Newton child on the left side. You can switch their places. It is not important. I know that the axis of rotation must be near the 400 Newton child, and it is all 2-meter long. But what's the distance? I don't know either of the distances. Before starting that, let's have another straight line. And this straight line is 3 meters long. And if I tell you that this part, the left part, is 1 meter, what is the length of the other part? You can directly tell me it is equal to 2 meters. But how did you find that? You will simply answer me that I subtracted the 1 from 3. So 3 minus 1 is equal to 2. So let's come back to the question. If I have this 2-meter long, if I say that this side is x, the 400 Newton side, the other side is obviously 2 minus x. And I have found their distances. Since the object or the seesaw is in equilibrium, their torques must be equal, so the net torque is equal to 0. Since I have only 2 torques and the torques are in opposite directions, so the torque of the 300 Newton child must be equal to the torque of the 400 Newton child, and torque is equal to force times distance. So the right side will be equal to 400 Newton times x, the left side will be equal to 300 Newton times 2 minus x. 300 multiplied by 2 and then multiplied by x, so I will get 600 minus 300x, which is equal to 400x. Now I will take the minus 300x to the other side. It will become positive. So the answer will be 600. That is equal to 400 plus 300x, which is equal to 700x. I will cancel the zeros. I will get x, which is equal to 6 divided by 7, which is equal to 0.86 meter. But let's remember that this 0.86 or x to be precise was from the pivot to the 400 Newton child. So I can say that the answer is 0.86 meter from the 400 Newton child. But that other distance was 2 minus x. 2 minus x was the distance between the pivot to the 300 Newton child. So we can also say that 2 minus 0.86 is equal to 1.14 meter from the 300 Newton child. So both answers are correct. The last topic in section 2 is moment of inertia. Let's remember some quantities from chapter 1, which we have studied their linear quantities, and then we have found their angular equivalences in rotational motion. So first was x. What was x in rotational motion? X was displacement or position. So we had theta or angular position or angular displacement. And instead of v, we had angular speed or omega. Instead of acceleration, we had alpha or angular acceleration. Instead of force, we had torque in chapter 2. We said that torque is the rotational analog of force. So what is the rotational analog of mass? Why mass? Because mass is the measure of inertia. So what is inertia? We learned inertia from Newton's first law, so we can define inertia as the tendency of an object to preserve its state of motion. So that is the first definition or explanation of inertia in linear motion. The second point, if we try to make any change, the inertia will resist this change. So we can also define inertia as the resistance to any change that happens in the motion. What kind of change are we talking about? Like speeding up, slowing down, changing direction. These are all changes that happens, and whenever we have these changes, we will see the resistance. Inertia only and only depends on mass, nothing else. The shape is not important, and the radius is not important. The type of the material is not important. The only thing that is important in inertia is only and only the mass of the object. We can say that as mass increases, inertia also increases. So the more mass I have, the more inertia we have. So it is harder to make any change. When we talk about the change, speeding up, slowing down, changing direction. So what is resistance in rotational motion? It is called as moment of inertia. So we can define moment of inertia as the resistance in rotational motion. And the symbol is I. Remember that, please. Some students will confuse the name as inertia because it starts with I, but please remember that I is called as moment of inertia. If you just say inertia, it is the resistance in linear motion. I is the resistance in rotational motion, which is a moment of inertia. And as the moment of inertia increases, it will be harder to make any change to the rotational motion of that object because as I increases, the resistance increases. So the rotational analog of mass is I, which is moment of inertia. So now we know that inertia depends only on mass, but what about moment of inertia? Moment of inertia depends on three things. It depends on mass, obviously. So the higher the mass is, it is harder to rotate that object because the resistance increases. And as radius increases, moment of inertia also increases. So it is more difficult to rotate that object or to stop the object if it is rotating. The last one is the most important one, which is the distribution of mass around the axis of rotation. So what do you mean by this? As the mass gets away from the axis of rotation, it will be much harder to rotate that object. So moment of inertia increases. And as the mass comes closer to the axis of rotation, it will be much easier to rotate that object. So we can say that the last point is talking about the shape of the object, like a hollow sphere, a ring, which we'll be talking about different shapes in a moment. So if we convert this dependence into equation, we will get mass times the square of the radius. So what about the last point? The last point will be C. So C stands for the distribution of mass around the axis of rotation. We can also define this constant before mr squared as the percentage of the mass that is at the farthest possible point. You will see that each shape will have its own constant, which will show the percentage of the mass that is at the farthest possible point. And the unit of moment of inertia will be kilogram, which is the mass, multiplied by meter square, which is r square. So we can say that as the mass is away from the axis of rotation or farther from the axis of rotation, it will be harder to rotate that object, or if it is rotating, it will be harder to stop that object. And Since it is harder to stop and rotate that object, the moment of inertia will be greater. And the vice versa is also correct. So we can say that if the mass is near the axis of rotation, it is easier to rotate that object. So the less moment of inertia we have. So each shape has its own constant. The first shape is point mass around an axis of rotation. Basically, it is a ball attached to a string and you rotate it in vertical or horizontal axes. The idea here is that all of your mass is at the farthest possible point. So C will be equal to 1. 1 stands for 100%, which shows that 100% of the mass is at the farthest possible point. The next one is thin hoop around a symmetry axis. This is important because we have two thin hoops. One of them is around symmetry axis and one of them is around the diameter. So the one that is around the symmetry axis has 100% of the mass around the axis of rotation, or at the farthest point actually. An example for the thin hoop around symmetry axis is a wheel or a ring. The next example is a thin spherical shell or hollow sphere around diameter. C will be equal to 2 over 3, which shows that 66.666 or 66.7% of the mass is at the farthest possible point. Examples for thin spherical shell is football. The next example or shape is disc or cylinder around the symmetry axis. So the constant will be equal to 1 over 2. 1 over 2 stands for 50%, which means that 50% of the mass of a disc or a cylinder is at the farthest possible point. Examples for disc are potter's wheel and merry-go-round. If you remember a moment ago, we said that we have two thin hoops. If we rotate the thin hoop around its diameter, then the equation will change because these 2 points are the only points that are at the farthest possible point, which will be equivalent to 50% of the mass. So C for thin hoop around diameter will also be equal to 1 over 2, which stands for 50% of the mass that is at the farthest possible point. The next example is a solid sphere around its diameter. C for this one will be equal to 2 over 5. 2 over 5 stands for, or will be equivalent to, a 40% of the mass. So if you have a bowling ball, the bowling ball's equation will be 2 over 5 mr squared, which means 40% of the mass is at the farthest possible point. Another example for solid sphere around diameter is Earth around itself. Remember that only use the 2 over 5 if it is talking about the rotation of Earth around itself. But if it is talking about the rotation of Earth around Sun, you have to use the point mass 1. The next example or shape is a thin rod around its end. So if we make one end as the axis of rotation, the constant will be 1 over 3. An example for this one, you can hold one end of the pen and drop it. You have just made the end of the pen to be axis of rotation. So, which corresponds to a 33% of the mass that is at the farthest possible point. Thin rod around the center will totally change its equation. If you hold a pen or pencil or a ruler at its center, the equation for the moment of inertia will be 1 over 12 ml squared. By the way, remember that you will take the whole length and not just from the axis of rotation. So C will be equal to 1 over 12, and 1 over 12 will stand for 8.33% of the mass that is at the farthest possible point.